So we're looking at Euler's method for the solution of a differential equation, and this method actually uses what's called first principles method for differentiation, which you would have looked at in methods. So this expression here, the way that this works, just quickly, is imagine that you've got a curve and we've got 2 points, we've got x and then some distance. This is going to be a distance of h, so this is going to be x plus h right here. So the 2 points on the curve, well, let's say that this curve is f of x. This point here, I'll just do it in a different colour, would be f of x. This point up here would be f of x plus h. Now to find what we call the rate of change, provided that h is fairly small, we can break this problem down into effectively a triangle and look at the slope between those 2 points. So the closer the 2 points are together, the better this approximation is going to be of an instantaneous rate of change. That means a rate of change at the point on the curve. So here you can see it's old school. It is actually going to be rise over run. And when we look at rise over run here for the slope, that's going to be our derivative. It is actually equal to the rise, which is f of x plus h. That's the high side. Take away this lower point, so that's going to be f of x, so that's the height of our triangle. And the width of our triangle, so this part, is h. So rise over run. And that's where this formula comes from. The derivative is approximately equal to, provided that h is small enough. Okay, the derivative is approximately equal to our function here that we put together. So this is what we call first principles. Now, for Euler's method, what we're doing is basically undoing this formula. So it's like the backwards derivative here, because we're integrating. We're trying to find a solution. Whenever we are trying to find a solution for a differential equation, we're always integrating. So underneath here you can see the same bits and pieces, this part, this part, this part, they've been rearranged. So all we've done is brought the h up to the right side and added the f of x on. This rearranged version is what we're going to use for Euler's method, and it is used to find approximate solutions. Now we know this is used to find approximate derivatives, so this is why our solutions using this method are approximate. So to use this you need really 3 things, well, actually 4 things I guess. The first 2 things, I'll count them as 2 separate things, the initial x value and the initial y value. So you need a point to start with. That's going to help us to pinpoint where our solution is going to be. You also need a step size. Now a step size is how much you're going to move incrementally. We're going to be talking about something called an iterative method. Now iterative means it repeats. Okay, so you can do it over and over again. So a step size is going to tell us how much we move up with each increment. And the last thing is you need to know the function that you're going to try and integrate, and that's our derivative. Now for this section and also in your CAS, the the function that you're going to integrate, we just call it g of x, but it's really f dash. So this is in your notes. You've got consider the differential equation dy dx equals cos x given y naught. Now the little subscript means initial. Given that y naught is 1, you've also got some other information in here. This is an x, so this is actually what we'd call our x naught, our initial x, which is 0. Okay, we're being asked to find y3. Now that is the 3rd term along. So we've got y0, we know that term. We're going to use a method that repeats to try and get y3. But we're going to have to find y1 and y2 on the way as solutions, because we find them, we can find y3. Now the bits in the question that we need, remember we need 4 things. We need an initial x, which we have. So I'm going to write them down. I've just given myself some space down here to write things. I've got my initial x, which is 0. That's that bit. I've got my initial y. I'm going to write that here as well, which is 1. That's that bit. I also know my step size. And the step size in the question is this h. h is always the step size. So h is 0.1. We're going to move up in 0.1 increments. We're trying to find y3. That's what I need. This is what I have, and I've written what I need. This part here is our differential equation. Now, we know from the notes just back a page that the differential equation, the f dash that we're trying to integrate, we're going to call that g. Okay, so in this example, our g that we're using is cos of x. And I'm just going to write down, I've got a table here, I'm just going to do it here as well. Because we're trying to find the third y value, we're also going to need to find the third x value, because that's going to help us. Now the cool thing about this is the x values move in a way that's predictable. They always move by adding h on. So we started with 0. If we add h, our next one is going to be 0.1. That's our next x. We're moving up in 0.1, so we're moving up in 0.1 for x. So the next one, once we add another h, is going to be 0.2. The next one, after we add another h, another step, is 0.3. So you can see here why we're going, when we find y3, we're going to have our x being 0.3. Okay, so I'm going to put that in this table. So there's a table like this in your notes, and we've got these already. So our job is going to be to find the other parts here. Now we're going to do that using this formula. Now this version is the version that's actually on your formula sheet. Okay, and the important part of this formula is this part here. I'll just draw a box around it. It's probably two parts, I guess. This part here too. This is how the x steps up. So we've just done that. That's that part there. So the part that we're going to use now is the part in the second box. This part. This tells us how to find our different y values, and you can see it involves the y that is the next one up. And in here, just to make life more complicated, in the new formula sheet, they've called this f. So even though your textbook calls this g all the time, in this formula it's actually an f. So you know what? I'm going to use an f so it matches the formula. Okay. So what we're going to do is use this formula now. I'm going to write it down so you can see how it works. And I'm going to write this down with my first term. The first version of this is when n equals 0. So let's write down everything. N equals 0 will make this little subscript a 1. It'll make that subscript a 0. H is a thing that we know. And this is going to be a little x with a 0 subscript. So what we're going to do is put in the things we know. We know what our initials y was 1. We know that h is 0.1. And we know that our function is cos x. Now, it's not the function of x, it's the function of x naught. It's not cos x that we're interested in, it's whatever x naught is. And we know that that is 0. So I'm going to pop that in there. So what we can do now is we can figure out what this is. 0.1 times cos of 0 is 1. So this is going to be 1 plus 0.1, so 1.1. So what that means is we've actually found our first solution up. So we already had one set of points given to us. We've now found our next one. Y equals 1.1 is the next solution up. Now we're going to repeat this process again. This time we repeat it with n equals 1 in our original red equation up here. So 1 plus 1 as the subscript is 2. 1 goes into the place where n is. H is going to be 0.1. The step size never changes. And it's going to be our function where we have x with a little subscript 1. Now the cool thing is, in this table I already figured out what my steps were and what my x's were going to be by going up with those steps. So I've already used this one and this one, so I'm actually up to this x now, 0.2. I know that y1, which is this one here that we just found, is 1.1. Plus we're going to have 0.1 times the function, which is cos x, but it's not x that we're looking at here, it's the next x up. It's going to be 0.1. So it's been one step up. Okay, so this is where you might like to use your calculator. I'm just going to open a calculator page. So it's just straightforward and putting in your equation. Boom. Now because this is all approximate, we can actually use decimal answers here. It doesn't have to be exact. Okay, so I'm lazy and I'm just going to put that there. Okay, so this is directly off my CAS. Beautiful. So this is actually my next y2. So my y2 here, I'm going to put 1.1995. Now what you might start to see here is you can see it's increasing. The reason for that is we're basically honing in on a solution. The more times you do this, you're actually going to get a better and better and better approximation to your final answer for y. Okay, so here we've only done 2 steps, but we are getting closer to where we want to get to. Here we're only looking at the third term. Okay, so we've got one more to go. So again, I'm going to do n equals, the next n that I have to do is n equals 2. So it's going to become a subscript 3. We've got y with the little subscript 2, because the n is 2, plus h, oops, which is 0.1, times my function, and this time it's not x0, it's not x1, it's x2. So can you see the pattern going on here? Okay, now we can substitute stuff in. I know y2 because I just looked it up. And again, the function here is cos. It's not x, it's x2. So I'm going to get that. It's my, remember that even though this has iterations, it doesn't really match what these are. This is x0, x1, x2, and x3. So we're going to look at now substituting in x2. So 0.2. Okay. And once we put that in, again, I'm just going to type this in my calculator. I can use the answer from the first part. And this is why the calculator is really good, because you can actually program it to do this method over and over and over again, as many times as you want. And I've got that answer, 1.29751. Okay, so I'm going to put that here at the bottom, see if it fits. Just fits. Okay, so that is going to be my answer here. So my third term is 1.29751. Now it hasn't asked us for any decimal places here, I don't think. No, so I'm going to leave it there. Probably, realistically 4 decimals for Euler's method is pretty good. Okay, so we've answered the question here. It said find y3. So to finish with, you have y3 equals, and you'd want to really just state that that's y3 at the end, and that's your answer there at the end. So Euler's method is all about using this formula. This is in your formula sheet, so you don't have to memorize it. You just need to know how to use it, and you need to know that the most important parts here is your initial y values and x values, your derivative function, and then being able to use this formula over and over again. It's a great idea, I find, to use a little table, or even like this if you want to set it up like that. Write down what you know and what you need, so you know how far you need to go. I mean, we went through y1, we had y2, and then we had y3. So we could keep track of what we were doing as we went. Okay, so that's Euler's method. The next part of this is going to be showing you how to program your calculator, and then I'll do the last couple of questions on the back of your worksheet.